What is up, everyone? It's Mr. Holtz, and today we're going to be looking at some practice problems for balancing chemical equations. So let's get started. So the first one we're looking at here is a synthesis reaction with chromium and oxygen where we're creating chromium oxide. Now, whenever I'm balancing a chemical equation, I'm going to show you guys the technique that I use. Usually we have this little yields arrow that kind of shows you the difference between the reactants and the products within your chemical reaction. And underneath that arrows is usually some open space if you have a blank page. So underneath that, I come up with kind of a table that shows me what are all of the elements in this reaction, and then I can balance to make sure that I have the same number of them on the left side as I do on the right. Because remember, the law of conservation of matter states that mass or matter is not created or destroyed, but it can change, right? A chemical reaction is all about changing form, but we're not going to lose any atoms and we're not going to gain any extra atoms. So it's really important to make sure that all of the atoms that we start with, regardless of what they are still in our reaction at the end, right? We don't want anything to disappear. So in looking at this reaction, we can see there's chromium and oxygen in our reactants, and obviously there's chromium and oxygen in our products. So since those are the only two things here, those are the only two things I really need to take into account, right? Chromium and oxygen. Now what I'm going to do here is I'm going to break them up so that I can write down how many chromium atoms do I have on the left side of the reaction, meaning how many do I have as reactants, and how many do I have as products. And I'll do the same thing with oxygen. Now, usually when I'm starting this out, I'm assuming that there's a 1 as a coefficient for all of these, and then we'll figure out how to change those to balance this out. So in looking at the subscripts, right now, this chromium on the left doesn't have a subscript, so we can assume there's only 1. And on the right side, our chromium has a subscript of 2. So already this atom here is not balanced, so we're going to have to change that. Oxygen on the left has a subscript of 2, so there are 2 oxygen atoms. And on the right, there is a subscript of 3, so there are 3 oxygen atoms. Now, in terms of figuring out which one of these numbers to mess with, as you guys get more practice, this will make more sense. But generally, see here how the oxygen and the chromium are by themselves. I'm going to balance these 2 coefficients last, so I'm going to mess with the chromium oxide first. Just because when I change these coefficients, when I change this coefficient, the only thing I'm changing is the chromium, right? When I'm changing this coefficient, the only thing I'm changing is oxygen. When I'm changing the third coefficient, I'm changing the number of chromium atoms and the number of oxygen atoms that I have in our products. So I'm going to want to mess with this one first. Now, since these aren't balanced as coefficients with all 1s, we're going to have to go up somewhere, right? Because coefficients of 0 won't make any sense. So I'm going to change this one to a 2, and then I'm going to have to readjust the numbers of atoms that I have in our products. So now that I have 2 over there, let's see how many chromium atoms I have. Well, if I have 2 molecules of chromium oxide, and in each molecule I have 2 chromium atoms, all I have to do is multiply our coefficient by our subscript to get the total. So in this case, I would have 2 times 2 chromiums, which would be 4, and 2 times 3 oxygens, which would be 6. Now, obviously, this is still not balanced, but let's move over to the left and see if we can balance some things out here. Well, conveniently, if we have 6 oxygens on the right, and this oxygen has a subscript of 2 here, all we need to do is make this coefficient multiply so that once we multiply the coefficient times this 2, we get 6 oxygen atoms. And if you guys figured that out, that would give us a coefficient of 3 here. So 3 times this subscript 2 now gives us 6 oxygen atoms on the left, which is good because that atom is now balanced. Now, can we do the same thing with chromium? Well, again, chromium on the right, we have 4 atoms, right? 2 times 2. And here we can change this coefficient from 1 to obviously any other integer. So in this case, we would want to change it to 4 so that we have 4 chromium atoms on both sides. And now we have a balanced equation. So our coefficients here would be 4, 3, 2. Okay, moving on. So this problem is actually a little special, and I'll point something out here that might be helpful to you guys. I'm going to switch over to blue. So one way, if you wanted to do this the same way that I created this table up here, you'd have to isolate everything. And there's a lot going on in this equation, right? There's aluminum, sulfur, oxygen, calcium, and hydrogen, okay? However, if you guys are confident or used to seeing polyatomic anions like this SO4 here, you guys might notice that the SO4, which is actually a 2- anion, this stays the same, right? It's always SO4 in the reactants, and it's always SO4 in the products. Now there is OH, but we'll take a look at that separately. So I'm going to keep this SO4 as one, not necessarily as an individual atom, but this ion stays together. And that's because this is a special kind of reaction called a double replacement reaction, where we're really just taking the cations of two different ions, or the positively charged ions, and we're just replacing them. So here we have aluminum sulfate as a reactant and calcium hydroxide. Now in the products, all we're really doing is switching the anions and the cations and getting two new compounds. So instead of having aluminum sulfate, we get aluminum hydroxide, and instead of having calcium hydroxide, we get calcium sulfate. So I'm going to keep the SO4s together. I'm going to keep the OHs together. And obviously, the only things that are left are aluminum and calcium here. Cool. So again, what do we have starting out? On the left, we have two aluminums. It's our subscript here. Remember, this 3 is the subscript on the outside of the parentheses. So this 3 corresponds to everything in this parentheses, which is the S and the O4. So technically, we'd have S3O12. But what this really means is we just have 3 of the SO4 anion. Okay. Calcium, subscript here is 1. So we only have 1 calcium. And again, this 2 is the same thing as this 3 in the sulfate. So this 2 corresponds to the whole hydroxide ion. So the OH, we have 2 of them total, okay? Now on the right, we have 1 aluminum, because that's our subscript here, 3 hydroxides, 1 calcium, and 1 sulfate. Now, the first thing that I notice is that the calciums are balanced, but we're probably not going to be able to keep that, because here, notice our sulfates, the SO4, is not balanced. So I'm going to want to balance that. Here, we have 3 of them, so I'll put a coefficient 3 here, and change my sulfates on the right to being 3. And now we have 3 calciums on the right as well. So we may have balanced our sulfates, which is good, but we have not yet balanced our calciums. So what should we do next? Well, it looks like we have an imbalance of hydroxides here. So notice how there's 2 on one side and 3 on the other. Whenever you have a 2-3 imbalance, the best thing to do would be to multiply them by each other, okay? So to do so, I would put a 3 in front of this 2 hydroxide, so our coefficient here would be 3, and I'd put a 2 in front of the one that has a 3 subscript, because 2 times 3 is 6, so that would balance our hydroxides out, but we will have to go back and take a look at our other atoms here. So on the left, we have 3 times our 2, so we have 6 hydroxides. And on the right, we have 2 times our subscript 3, which is, again, 6 hydroxides. So let's go back and check. We change the calciums on the left, and we change the aluminums on the right. So here we have 3. Our subscript for calcium is 1, so we have a total of 3, which is good because this looks balanced now. And aluminums, we have 2 times our subscript 1, which is still 2. So our aluminum looks good. Now, sometimes we'll have to go back and change these if we have to erase the checks if this coefficient here doesn't balance the whole thing. But let's see what we might need here to solve that. Oh, it looks like it's already solved, right? Our hydroxides are balanced and everything else is balanced. So it looks like we only need a coefficient here of 1. So our coefficients to balance this double replacement would be 1, 3, 2, 3. Awesome. Moving on. So this here is a combustion reaction, and the reason that I know this is a combustion reaction is because I have some kind of hydrocarbon as one of my reactants, along with oxygen, and what we're producing is carbon dioxide and water. So if you guys have put anything glass at room temperature over like a candle flame, you'll notice some condensation because it's releasing water from that reaction. So this here is an example of a combustion reaction. Now in this case, I am going to separate all of my elements because unlike the last problem, I don't have any polyatomic anions. There aren't any compounds here that are staying together throughout the reaction. So I notice here I have carbon, hydrogen, and oxygen. And it's the same thing on the right, right? Carbon, oxygen, hydrogen. And obviously the oxygen shows up in 2 places, so we'll have to take that into account, but it's still the same atom. So we have carbon, hydrogen, and oxygen. And again, I'm just going to count up how many of them I have on each side, and then we'll go from there. Now, in this case, I'm probably going to balance the oxygen as this O2 last, because again, that's the only molecule here where the coefficient is changing one atom. Obviously, in the rest of them, I'd be changing 2 atoms. So how many do I have to start out with everything? I have 6 carbons on the left, 6 hydrogens on the left, and 2 oxygens on the left. On the right, I have 1 carbon, I have 2 hydrogens, and adding this up, I have 2 oxygens from CO2 and 1 oxygen from H2O, so I have 3 here. So again, we'll have to mess around with this to try and balance out this 2, 3. So just to start out first, I'm going to try and balance out our carbons, and then we'll go from there. So to do that, I would put a coefficient 6 here, right? Because we have 6 carbons on the left. So this changed the number of carbons on the right to being 6, and it changed our number of oxygens on the right to being 1 plus the 12 that we now have here. So we have 13. Now this is going to be an issue, and I'll point it out why now, but we'll have to change it later. Notice that on the left, we only have O2. So anytime we have a coefficient here that's a whole number, right? It could be 1, 2, 3, 4. Any of those numbers times 2 is always going to be an even number. So we're probably not going to ever want an odd number of oxygens on the right side. So now that that's tripping things up, I'm going to go back and change these coefficients and multiply the first carbon by 2 and then come back and change them. So I'm going to put a 2 here because I know that will get me to even numbers. So let me change that. That adjusted how many carbons and how many hydrogens we have on the left. So now we have 12 carbons, right? 2 times 6, and 12 hydrogens. So what I'm going to want to do here is multiply this by 12, right? Because previously we tried to multiply it by 6, and that didn't seem to work. So that's going to change our carbons and our oxygens here. So 12 times our subscript of 1 gives us 12 carbons. These guys are balanced, so that's good. But again, we might have to come back and change that later. 12 times our subscript of 2 is 24, plus our 1 oxygen here is 25, which again, isn't good yet, but we still haven't balanced the water molecules, so let's give that a shot. Well, now that we have 12 hydrogens on the left, we can put a 6 here, right? And that 6 will change not only how many hydrogens we have, but also how many oxygens we have on the left, or on the right, excuse me, because these are our products. So 6 times 2 gives us 12 hydrogens. Cool, these are balanced now. Now, how many total oxygens do we have on the right side of the equation? Well, we have our 12 times 2, which gives us really 24, plus our 6 from water, so plus 6, which gives us a total of 30. Okay, that's good because that's an even number. So what are we going to want to use for our coefficient here? Well, if we're multiplying by 2, we should probably put 15 here, because 15 times 2 is what gives us 30. Now everything is balanced, which is great, but what we should really be checking here is, are these the lowest common denominators that we can use for all these coefficients? Meaning, if these can all be divided by 2, then we can simplify that equation. Now in this case, that's not possible because we do have an odd number here, right? And we can't really use 7.5 as a coefficient because we can't have half of an oxygen molecule. And it doesn't really work that way. So in this case, we do get the coefficient 2, 15, 12, and 6, and that ends up balancing out and giving us equal amounts of everything on both sides. Awesome. Got a couple more practice problems here. So now we have a decomposition, and this is a decomposition reaction because we have one reactant decomposing or breaking down into form 2 different products. Okay? So notice here the only things we have are phosphorus and oxygen. So in terms of figuring out numbers of those, on the left we have 2 phosphorus atoms and 5 oxygen atoms. On the right we have 4 phosphorus atoms and 2 oxygen atoms. So for changing our coefficients here, I'm probably going to want to balance my phosphorus first just because that jumps out at me. So I'm going to put a 2 in front of this one, in front of our only reactant, and that will change both of our reactant atoms. So we'll give us 2 times 2, which is 4 phosphorus atoms, which is good. This is now balanced. and it gives us 2 times 5, which is 10 oxygen atoms. So that's good for phosphorus. I'm going to leave this coefficient blank here until we're finally done. But can we change our coefficient for oxygen? Well, if we have 10 on the left, we can multiply this by 5 here. And because our subscript is 2 after the oxygen, 5 times 2 is 10. So this is happy with a 2 here and a 5 in front of the oxygen, which means our coefficient in front of phosphorus would just be 1. So we get the coefficients 2, 1, 5 here for this decomposition of diphosphorus pentoxide. All right, last one. And again, if you guys are taking note, this is another, just draw a little dot here so I can scroll down a little more. This is another double replacement because we have aluminum with bromine switching to be aluminum with chlorine, where the chlorine's by itself first, and then the bromine's by itself afterwards. But in this case, because all of our ions are monatomic, or they're dealing with one individual atom, I'm not going to be able to do the same thing that I did up here with our sulfates, because obviously not all the atoms are staying together in this example. So the way that I'm going to separate these would be aluminum is in one of these, bromine is here, and chlorine is here. So that accounts for all of the different kinds of atoms in this double replacement. Now, how many of them do I have on each side? I have 1 aluminum on the left because our subscript is 1, 3 bromines, and 2 chlorines. On the right, I still have 1 aluminum. I have 3 chlorines because of this subscript 3 here, and I have 2 bromines. Now, again, we're dealing with some 2s and 3s here. So let's start messing around with it. And if I were you, again, I'd probably balance our Cl2 and our Br2 last, just because those are by themselves. And again, the only things they're going to change are the chlorines and the bromines respectively. So since I have 3 bromines on the left and 2 bromines on the right, I'm going to try and move both of those to get to 6. So if we want to end up with 6 on both of these, I'm going to need a coefficient of 2 on the left, because 2 times 3 is what gives us 6. And I'm probably going to need a coefficient of 3 on the left. Now, again, that doesn't help us with filling in the coefficients for the bromine and the chlorine last, but if it works out, that will be convenient. So 2 times 3 is 6, 3 times 2 is 6. Bromines are looking good. Now, obviously, this changed how many aluminums I have. So in the left, we're going to have 2 aluminum atoms. We still have 1 on the right. So if we're going to want to balance that out, again, with the chlorine, we have 2 and 3 here. So let's try 2 here. And I think that's going to be conveniently fixing all of our problems. So it's going to change how many chlorines we have and how many aluminums we have. So obviously 2 times 1 would give us 2 aluminums, which balances this out, which is great. Now 2 times our 3 subscript for our chlorine gives us 6. Obviously this is not balanced, but again, we can fill in our chlorine coefficient last. If we want to balance out 6 chlorine atoms, then we can put a coefficient of 3 here, and obviously 3 times 2 gives us 6. So all of these atoms are now balanced out. So our coefficients here for this double replacement would be 2, 3, 2, 3, and I hope those were helpful.